flow computer models. Our previous final difference model of Laplace equations was very well behaved and converged nicely with or without over-relaxation. Much more care is needed to model the full Navier-Stokes equation. The challenges are quite different and they have been met to a large extent, so there are now many textbooks that use computational fluid dynamics. This is not a textbook on CFD, but we will address some of the issues in this section. One-dimensional unsteady flow. We begin with a simplified problem showing that even a single viscous term introduces new effects and possible instabilities. Recall the previous chapter where a wall moves and drives a viscous fluid parallel to itself. Gravity is neglected. Let the wall to be the plane at y equal to 0. Moving at the speed of 0t, a uniform vertical grid of space delta y and has a node at which the local velocity u and j as shown in this picture, where the subscript j denotes the time step j delta t. The wall is n equals to 1 if the velocity profile be a function of y and t only, and 0 continuity equation for the incompressible flow is satisfied, and we need only solve the x momentum, which is where nu equals kinematic viscosity. Utilizing the same final difference approximation, algebraically we can write the final difference time forward for a central spatial difference form as for the momentum equations u n j in time, and in the location spatial we need to change the n denotes the location of the nodes, Rearranging, and found that we can solve explicitly for un at the next time step. So un in the next time step un and sigma does u at the node n at the next time step j plus is a weighted average of 3 previous values. We can write the velocity at node n at the next time step j plus 1 is a weighted average of 3 previous values. Values similar to the 4 nearest neighbors average in the Laplacian method in the previous derivation. This equation, since the new velocity is calculated, is called an explicit method. It differs from the well-behaved Laplacian method, however, because it may be unstable, the weighted coefficients must all be positive to avoid divergence. To avoid divergence, now sigma is positive, but so we had the weighted kinematic viscosity on but may not be greater power down 0, so we can obtain another relation for sigma. Normally one would first set up to the mesh size delta y. To avoid divergence, we should choose the appropriate size of delta t and delta y. There is an alternative implicit approach. Let me write an implicit approach. In many finite difference problems, stability limitations such equations where sigma greater than 0 and 1 requires an extremely small time step to allow larger step. One can react the model in an implicit fashion by evaluating the second derivative model. At the next time step, we can write this relation for the momentum in x direction time derivation and spatial derivation This rearrangement is unconditionally stable for any sigma, but now we have three unknowns in this expression: minus plus 1 the j plus 1 velocities, the velocities as in the time step j plus 1 are our unknowns. This is an implicit method. Meaning that one must solve a large system of algebraic equations for the new nodal values as time j plus 1. Fortunately, the system is narrowly banded, with the unknowns confined to the principal diagonal and its two nearest diagonals. In other words, the coefficient matrix is 3 diagonal, a happy event. A direct method called the triangular matrix algorithm three diagonal matrix algorithm TDMA is available and explained in the various references. If you have not learned TDMA yet, converge satisfactorily by rearrangement and iterations. This expression unj plus sigma un minus all 1 plus 2 sigma at each time step j plus 1 sweep the nodes over and over using this equation until the nodal values have converged. This implicit method is stable for any sigma, so we can write the stable for any however large. To ensure accuracy though, one should keep delta t and delta y small compared to basic time and length scale of the problem. This other habit is to keep delta t and delta y small enough that nodal values change no more than 10% from the nodes n and g to the next. So implicit method in the numerical solution is stable for any values of sigma. The next subsection is steady two-dimensional laminar flow.